Okay, good morning, guys. Welcome to the Bureau Seminar Series. Today we have Adam McArthur from University of Leeds. So before we start, I would like to remind you that this talk contains some proprietary data. So only us can record and should record. So hopefully no one else is at your end or at your home record this video. And we will do some blurring and then publicize later at YouTube. So the first 30 minutes, those contents will be available at YouTube. So I will give you a brief introduction of Adam. Subsequent to some time in industry, Adam was awarded a PhD in sedimentology and palynology from the University of Aberdeen in Scotland. Following this, he led a research group in Brazil at the University Federal do Rio Grande do Sul in Porto Alegre, developing new tools to investigate deep marine stratigraphic architecture, where he pioneered the use of Palynofacies in deep water. He's now a co-investigator in the turbidite research group at the University of Leeds, where his main research interests are interaction of sedimentation and tectonics, submarine sedimentary processes and products, and marine micropaleontology. So Adam, the rest is yours. And if you want to have your connection, you can, turn off your video if you would like.
Yeah, I'll do that once I get going with the presentation. Thank you for the introduction, and thank you for the interest in the research and for inviting me here. Yeah, thanks again for the interest in my research on understanding and classifying deep marine depositional environments with Palynofacies. And today I'm going to show you how we develop the methodology, firstly from world-class outcrops, and then with a brief example of how we applied this in the subsurface. I'd just like to thank my colleagues and co-authors on this endeavour, both at the Universities of Aberdeen and Bologna and at the Federal University of Brazil, where I was based during this research, and also the company sponsors, Shell. So in this talk, I will cover a range of deep marine environments, covering channel-levee complexes, and we'll take a look at their stratigraphic architecture, and then the type of Palynofacies, or the particulate organic matter that are preserved within such sediments. Then we'll take a look at some intraslope type depositional settings, again, the sedimentology of it, and then the Palynofacies. And finally, take a look at some basin-floor fan examples before considering the implications and potential applications of this method. This was a 3-year project with the aim to develop new tools to investigate depositional environments in deep marine settings. The hypothesis that we aimed to test was whether organic matter would vary within deep water depositional environments. And in order to develop this new method, we visited well-known outcropping systems where we had a high confidence in placement within the depositional system. So I guess you guys are mostly experts, but for the unintuited in the audience, then basically by deep marine, we're talking about generally greater than 200 meters of water depth. So once we're off the continental shelf into the slope and abyssal plain type environments. And we have a huge variety of processes, sedimentary processes that occur in this setting, and also a large range of depositional environments and sub-environments, which we can relate into architectural elements in the subsurface that we might hope to recognize either at outcrop or in the subsurface. And each architectural element, so by that I mean things like channel axis, off axis, levees, and their different components, they each have different properties, different sedimentological properties, but they're also significant for the subsurface in terms of building reservoirs and so on. So gaining as complete an understanding of these systems as possible is essential to help understand what's happening in the subsurface, build reservoir models, and so on. So what I'm going to do for you today is take you to a range of case studies across the world. Firstly, we're going to head fairly close to you guys, at least closer than I am, into Baja California in Mexico to look at a slope channel-levee system of the Rosario Formation in Baja California. So this is a latest Cretaceous to Paleocene system that crops out in the peninsular ranges on the west coast of Baja. And the sediments here were deposited in a four-arc basin on the Pacific margin in bathyal water depths, so at least 1,000 meters of water depth. And although a range of channel systems, channel-levee systems have been recognized along this margin, here we're going to focus on one of those, the San Fernando channel-levee system, which particularly with one of the co-authors on this work, Ben Neller and his group, we have more than 20 years of detailed research, high-resolution mapping of the stratigraphic architecture and so on, to give us confidence in the constraint of the depositional environments. Briefly, in this system, what we recognize is a large incision, essentially a canyonized type system, and then a series of channel complexes that infill that incisional surface, representing repeated channel cutting, fill, and abandonment, with a genetic external levee developing as the conduit became filled. And here's just a summary representation of how that looked like on the seafloor. We also recognize that mass transport deposits represent a significant component of the channel fill. The reason that we went here, in addition to the extensive research, is that the fantastic quality of the outcrops, which are amongst the best in the world, surely, for channel levee systems. Essentially, the modern day arroyo runs parallel to the ancient channel axis, allowing us to move longitudinally up and down the axis of the channel. And then all of these little side gullies and valleys allow us to go off into the various overbank type settings as we move away from the channel belt. This allowed us to collect a number of sedimentary logs through that system, as I said, from the axis of the system into the off-axis and various overbank type settings, and to conduct high-resolution sedimentary logging and collect samples at regular intervals, specifically really from the turbidite component of the mudstones throughout this system. And I'll just run through the different architectural elements there that we recognize briefly. So we have our channel axis, where we have the thickest beds with some strong erosion surfaces within them, often quite coarse-grained, but with some finer-grained, perhaps bypass-related fills that we can target sampling. Then within our channel belt, we have areas that we're defining as the terrace, where we have quite erratic bed thicknesses, normally fairly tabular beds that may show a range of reflection structures and so on within them. And moving into internal levees within the channel belt, and then the major external levee, where we have large-scale outcrops, and we can trace thinning and pinching of beds away into the various outer external levee environments that become ever more finer-grained, thinner-bedded, and muddier as we move out into the background deposits, which are dominated by hemipelagic mudstones, which represent shutdowns of the system. So, Palynofacies is the microscopic study of particulate organic matter contained within a sediment or rock after acid maceration. And this method has commonly been applied in terrestrial and shallow marine systems for paleoenvironmental analysis, but had hitherto not really been applied in the deep water setting. It's quite a simple process. So what we do is take 10 grams or even 5 grams is suitable of clean, fresh rock sample, and that we process in a fairly simple way with non-abrasive, non-oxidizing treatment. So simply hydrochloric and hydrofluoric acids are applied to the sediment overnight, and then we sieve the samples to collect the organic matter, and then produce a microscope slide and conduct an analysis of at least 300 particles per sample to make them applicable for statistical investigations. And what we recognized from the channel-levee system is a wide range of organic matter types, both terrestrial debris, so wood of varying degrees of preservation, then things like leaf debris, of course, pollen, spores, and so on. And then some marine material as well, so things like dinoflagellate cysts, marine algae, and amorphous matter that's normally associated with phytoplankton debris in the marine environment. And the question is whether variations in the abundance, the size, the proportions, and so on of these particles could be related to the various sub-environments that we were just looking at when we collected the samples. What we've seen is that we can recognize 7 different Palynofacies associations corresponding to the architectural element, minus the debrites that showed a more sporadic type of distribution. What we see is that the deposits from the channels have the largest fragments of dominantly terrestrial organic matter. And then we see a decrease in particle size and proportion of the terrestrial to marine particles as we move away from the channels into the various overbank type deposits until we're into the hemipelagic deposits that are dominated by the marine amorphous organic matter. We're fortunate in this general system to be able to take samples through a range of about 5 million years, and we didn't see any major temporal variation associated with the deposits. It gives us some indication that we might be able to use this in other systems. Obviously, these are quite complex signals that are coming through, so it was appropriate to use some multivariate statistics to investigate the different groupings. What you'll see here is principal components analysis and some detrended correspondence analysis of the samples. And in there, we're able to define loose groupings that are to an extent gradational, but show a transition from the channel axis through the various overbank settings out into our hemipelagic type deposits. But these are very gradational and quite loose groupings. So it's also appropriate to apply what's known as fuzzy clustering to these sorts of data sets. And just as a brief explanation of fuzzy clustering versus your traditional sort of hard statistical clustering, then in traditional clusters, each sample will be assigned to a cluster, and that's a hard grouping, whereas in fuzzy clustering, each sample is proportionally assigned to each cluster. And the result are these mixed or fuzzy groupings that we can use to investigate the data set and to give us more control on the variable factors in each of our sub-environments. And here I hope you can see that the proportions to which each sample belong to each of the clusters is variable, and it gives us some confidence that we can start subdividing our various sub-environments based upon their organic matter. But we also need to consider the particle size, shape, and diversity, and so on, in order to develop our model for the distinguishing different depositional sub-environments with Palynofacies. And what we can see from our model is that the channel axis contains the largest, densest particles, with the finer fraction inferred to have either been bypassed further on downstream, as we'll look at later, or indeed carried into the overbank type settings, where we see ever finer, lighter, and more elongate particles being deposited as we move out into the overbank, and an eventual mixing with marine matter as the flows likely became diluted and mixed with ambient water. So moving swiftly on down the slope, then the next area that we're going to look at is confined interslope settings. The confinement on the slope can occur through a variety of mechanisms, be it tectonic, for example, in the alpine basins that we're going to look at shortly, but it could also be due to diapirism, mud diapirs, and or salt diapirs that are, of course, very common in the Gulf of Mexico and elsewhere. The result of this confinement is a complex seafloor bathymetry, the interaction of which with turbidity currents creates an even more complex depositional system, a wide range of architectural elements in these types of settings. So in order to examine some of these, we're going to go now to France, particularly southeast France, into the alpine basins, and very specifically, we're going to look at one of the outcropping basins, and the Eocene-Oligocene age Pierre Cava system that crops out in southeast France, which is a really classical area of deep water sedimentology. It's where Arnold Bauma and others worked on the ideas of the Bauma sequence, of course. And the reason for that is that we have these really spectacular outcrops of deep water sediments where you can trace beds along the basin, and it provides these really excellent seismic scale exposures to go and work on and have some certainty in the depositional setting. We recognized 8 key sections to go and work on in a relatively proximal setting in the south to a relatively distal setting across the basin, in which we can log hundreds of meters of strata and collect hundreds of samples across a range of architectural elements at a sort of bed for bed type scale, at least on the key marker beds that we can recognize across this basin, as I've said, which gives a general proximal to distal trend across what's the preserved extent of the basin. So again, just to quickly run through the type of sediments and interpret their depositional environment, then we have firstly these very thick bedded, up to 25, 35 meters or so thick sandstones, which show often normal fining. They can have an extensive mud cap, meters thick mud cap at their top, and some significant scour on the base, which can often show a debritic component. And these events thin very rapidly northwards and would be interpreted as single events, filling the scours at the slope. Then we still have meter thick, coarse to fine graded sandstones with medium to thick mud caps above these. They display a range of sedimentary structures and often have internal debritic components, and in places show flow hybridization. But as opposed to the more extensive deposits at the base of slope, these show a good continuity across the basin, although becoming thinner northwards. Also present across the basin are thinner bedded, more mud-rich intervals, which do become more prevalent towards the northern end of the basin. These have a range of structures within them, indicating some potential reflections, reflected flow structures, such as this beautiful example here, and often have thick mud caps, indicating that they were deposited in a fully confined basin and were feeling nearby relief. And then the last element that we looked at and sampled are these, again, thinner bedded deposits, but within which you can see termination and pinching out of beds onto a regional slope, and occasional remobilization, slumping and sliding and so on, implying deposition adjacent to or near the basin margin, which is what we'd interpret this last element to be. So we collected, again, hundreds of samples through this system, and in this case we're able to recognize 8 different Palynofacies associations. Here again we have all the types of organic matter that we recognized, going from the denser terrestrial material to the marine material, and this shows various proportions in the various environments that we have looked at. To look at that visually, then what we see is in the proximal sheet deposits and the megabeds, we have the largest and densest particles being preserved, and a transition to the lighter terrestrial fraction as we move more distally into the basin, where it becomes dominated by the lighter terrestrial fraction. Whereas the distal heterolithics and the on-lap deposits show a much greater proportion of the marine matter, likely as the flows again became diluted and mixed with the ambient material that was in the basin. Here the deposits were very gradational, as likely as the flows spread across the basin. So again, it was appropriate to use our fuzzy cluster analysis, from which we can again get quite a clear distinction of our various depositional environments based upon their organic matter. But again, we need to consider the particle size, shape, and diversity of the linomorphs and so on in order to provide a classification that we might use in order to recognize that the largest and densest particles are occurring in the most proximal settings, and likely due to the fractionation of material as flows traversed that basin, we see a transition to the lighter and also more elongate and platy type of particles as we move across the basin, and then a mixing with the marine material, the dinoflagellates, algae, and amorphous marine matter as we move towards the distal ends of our basin. So continuing on now past the slope and onto our abyssal plain type of deep marine setting, then we're now looking at basin floor submarine fans, which are particularly common in our larger passive margin type settings, where we have a natural and unconfined route of turbidity currents, allowing the construction of large-scale submarine fan systems, for example, as we see on the modern-day Atlantic margins. A relatively smooth seafloor allows run-out of flows for hundreds of kilometers and can give us some of our more classical submarine fan and lobe type elements within these types of settings. And in order to look at one of these systems at outcrop, we went to Italy this time in the Apennine foredeep, which is deposits of which are now exposed in central Italy, of the Marnoso-Arenacea Formation, which is quite well known as a excellent representation of deep water sediments that were deposited in the foredeep to the developing Apennines. There's a range of stratigraphy that spans around 4 kilometers, and here we're going to focus on the lower, less confined of those systems that were deposited in an elongate foreland basin that became ever more confined through time until its eventual closure and obvious uplift to the exposed sediments at outcrop today. The sediments, at least the siliciclastic turbidites, were primarily sourced from the north, from the Alps, But we also have a series of mass transport deposits coming in from the growing Apennine thrust front, and also some calci turbidites coming in from the south, act as quite nice marker beds within the basin. And what we had in this setting were very large, efficient flows spreading across a relatively unconfined basin. And previous workers in there have been able to correlate on a bed for bed scale across more than 120 kilometers downstream in order to give us some really nice framework to go in and sample in this type of setting and recognize a range of depositional elements, and again collect hundreds of samples to test what the organic matter looks like in this type of setting and how it may vary across the system. So to run through the depositional environments that are recognized here, then we want to think of the classical sort of submarine fan type of environments. So using the models of Prelat and Gronenberg, then what we can think of is essentially the submarine fan as a whole, and with a range of sub-environments, the fan fringe, then into individual depositional lobes, their axis, off axis, and so on. So firstly, to look at the deposits of the lobe axis, then we have these thick beds, the highest net to gross, the highest sand proportion, and these deposits, which are often amalgamated, and we see various traction structures towards the tops of beds, but they're often dewatered, and they may show both a vertical but also lateral transition into thinner bedded deposits with a slightly lower sand content. Mud caps may be present now, and a lot of traction structures we would interpret as being the deposits of a lobe fringe. Mud-rich intervals between lobe complexes can often be hard to distinguish sedimentologically, but here we can define interlobe deposits, so the muddier deposits between individual lobes, as having a very low net to gross, being very thin bedded, muddy, silt dominated, and with occasional rare thin sandstones. But the key to these depositional environments is that they're entirely dominated by turbidite mudstones rather than having any real significant hemipelagic mud component. And they also show intense bioturbation. Then moving beyond the lobe elements into the fan fringe in general, we have obviously a lower sand content beds. And here we have a significant component not only of turbidite mud that you might see in the darker intervals here, but also this more blocky homogeneous mudstone that we can relate with the hemipelagic component. We do have sporadic sandstones in here, and also sporadic hybrid event beds that I'll not go into in any great detail here, but they're another full marker of the environment. Then as we move really beyond our fan and into the basin plane, then what we have is significant intervals dominated by mudstone, very low net to gross, and with rare thin-bedded turbidites coming in here, but a real dominance of hemipelagic mudstones throughout that interval. And then the final element that we looked at in this setting are condensed sections, which are almost entirely represented by hemipelagic mudstones. Some of these intervals that you might think to be thicker sands in here are actually just more concreted intervals. This is essentially 99% mudstone with very rare thin turbidites that manage to get up onto these areas that we interpret as being the result of deposition over structural highs or mass transport deposits that were creating significant seafloor relief. So again, we collected hundreds of samples through this system and subjected them to the same type of analysis to look at their organic matter content. And again, we had similar types of organic matter to the other systems, but pleasingly showing different proportions of these. However, in all cases, as you'll get a feel for here, they're now dominated by the lightest terrestrial proportion. And we recognized a range of very gradational Palynofacies associations relating from the proximal lobe axis through various environments into the background type of basin plane element, but still really dominated by the light terrestrial fraction. So in this case, again, it was particularly important to use this fuzzy clustering technique to try and give us some insights and some confidence in the use of this classification scheme. And again, we can see the various proportions of the types of organic matter in the different clusters give us some confidence that we can use this system to classify the different depositional environments based upon their organic content, and develop a model for the type of organic matter that you might expect to see in the different environments as flows ran out across that basin plane. So to summarize the development of the methodology, then we looked at slope channel-levee systems, the Palynofacies of which were largely dominated by terrigenous particles. They show a very poor sorting, and overall the largest and densest particles of any of the deep water systems, with a gradation towards lighter material and more marine matter as we move away from the channel into the overbank and background slope deposits. We then looked at some confined intraslope deposits, which actually show the poorest sorting of the organic matter. We have a mixing of both terrigenous and marine matter, as all particles entering that basin became trapped there. And then we moved on down to the basin floor to look at a submarine fan system, which is dominated by the lightest terrestrial fraction, but was relatively well sorted as such, with decreasing particle size as flows ran out across the basin plane to merge with the ambient marine material. But of course, I'll just highlight that we should, of course, use all information, sedimentological, petrophysical, geophysical, and so on, to formulate our ultimate interpretation. So I'm just suggesting this is an additional tool that can be useful, I'd say particularly in thin-bedded, mud-dominated type systems. So briefly to think about what might be controlling the distribution of the organic matter in these settings, then I hope that you've seen a clear differentiation of the organic matter assemblages as we move away from sediment conduits. And with our siliciclastic component, the grain size essentially is often a function of density and sorting of siliciclastic material. That's quite well understood within turbidity currents. And what we can postulate here is whether there's a similar sort of hydrodynamic fractionation effect upon the organic matter within a flow, with the denser material being first to be deposited, and the ever lighter fraction being carried in suspension as flows pass through their various depositional settings. And that's something that we're doing some laboratory modeling of just now to try and understand the settling velocities and so on of the organic particles we see in these systems. Now to think about some potential applications of this work in terms particularly of helping resource exploration, then Palynofacies has already been used to great success in terrestrial and shallow marine environments. And these pilot studies, I hope, showed that in deep marine settings, we can start using Palynofacies to differentiate different deep water architectural elements, which I'm sure you appreciate is not always easy in the subsurface. So we trialed this methodology in a couple of locations, both offshore Brazil, where I was based at the time, and also offshore East Africa, that I'm going to show you some examples from today. And I'm afraid for those of you that are watching on YouTube, then we're going to have to blur out the next couple of slides to protect some proprietary data. But the ultimate goal here was to apply the Palynofacies classification to a subsurface dataset in order to exploration and development. And this was applied to samples from offshore of Tanzania, specifically from the Mafia Deep Basin, which is a frontier exploration area with very limited public data, but within which we know that we have a series of turbidite clays that have been recognized in the Cretaceous to Paleogene, through which we may recognize a series of channel-like bodies in the subsurface using 3D seismic data, but also a series of distributary elements within those, and identifying which depositional environment is quite tricky, particularly in the thinner bedded intervals that are encountered in wells. Are these levees to some of these channels that we see running through the data sets, or were channels incising older lobe or sheet-like deposits? And so we were tasked with using the Palynofacies methodology to apply to assist the reservoir modeling in this area. And here, 50 ditch cutting samples were analyzed in order to assess their impact on the development strategy of hydrocarbon fields in this area. The key question was to determine the nature of low gamma ray response intervals that both bound the main reservoir interval and also occur within that reservoir interval. Are these interlobe deposits, levee, mass transport deposits, and so on. And this has fundamental implications for the distribution of the thin beds. Are they laterally extensive? Are they acting as barriers or baffles to fluid flow through the reservoir? So there are, of course, a number of challenges with applying this methodology in the subsurface, primarily in the suitability of using cuttings from wells rather than the certainty that we have in the depositional environment from outcrop. Also concerns with contamination from drilling fluids, alteration of the samples, and so on. Although I'll highlight that in our example from Brazil, we were able to use core material to at least have some certainty. This material wasn't entirely mixed and had some sedimentological criteria to identify the settings. That wasn't the case here, where only ditch cutting samples were available. What we found in the samples were excellent preservation and good recovery of the organic matter within the samples, which were rich in marine matter, but also show various influxes of larger terrestrial matter, such as this degraded wood. Again, we can use the proportions of the organic matter and compare those to the classification schemes that we developed from the outcropping systems in order to try and classify the depositional environments in the subsurface. And of course, we can integrate that information with the geophysical, petrophysical data, and so on, in order to maximize the impact for reservoir modeling. What we can see when we look at all the different types of organic matter through the well sections is that we have a lower interval that's quite mixed, quite a lot of the light terrestrial fraction, but also marine matter, and shows us some affinity with the confined intraslope type deposits. Then after a break in the system, where we see a more shutdown type signature, then we see a more mixed system, but with higher proportions of the denser type of ferruginous organic matter, particularly in this lower sample, indicating that we might have a change into a more channel-levee type setting. Again, we can run some statistical investigations on these data sets in order to have some confidence. And what you can see plotted here are in yellow are all the outcrop samples from a channel-levee system, in blue those from the intraslope setting, and in orange the basin floor fan settings, and then these turquoise dots are from the subsurface system. So what we see from that is that they have a relationship with both the channel-levee and confined basin settings. And so we were able to make some interpretations, also integrating some of the petrophysical and geophysical data in order to recognize the lower interval of the reservoir as being affiliated with confined intraslope type turbidite deposits. Then in places we have a shutdown of the system represented by some hemipelagic deposits, which were incised by a channel system, which eventually was overtopped by a genetic levee, and that higher gamma ray muddier intervals within the reservoir interval showed a very mixed assemblage, and we can associate those with the deposits from debris flows within that channel system that might then act as more baffles rather than real barriers to flow through that system. So just to summarize for you then, I hope what I've shown you is that turbidite systems are important exploration targets for deep water hydrocarbon prospects, but present significant complexity in their sub-environment. Utilizing more than 700 samples from world-class outcrops, we've developed a new tool to identify deep marine archaeological elements based upon their particulate organic matter, or their palynofacies. The distribution of organic matter is not random in turbidite systems, with the density sorting of organic matter controlling their distribution in a similar, but actually more complex fashion based on stochastic particles. This relatively low-cost scheme can now be applied when integrated with subsurface data in order to assist reservoir characterization, understanding of which is crucial for well planning and prospect risking, both in conventional and unconventional field development. So I'll just finish off by thanking the sponsors of this work, and also to all the guys that helped me in the field and the laboratory, and I'm more than happy to take any questions on that.
All right, thank you, Adam. Any question from the audience? You're welcome to use the chat or unmute yourself.
Yeah, I have a question.
Hi, Robert. Robert.
Yes. Most of your studies were on Cretaceous and Cenozoic rocks. Do you think this would have an application to the Paleozoic as well?
Yeah, basically, as long as there's going to be life forms around, then it should be applicable. Obviously, the types of organic matter is going to vary slightly, so it would need to be thought out. You couldn't just apply the exact same categories of organic matter as we've done here, but I don't see a reason why it wouldn't. I have worked with, say, carboniferous systems in the past that show actually relatively similar types of organic matter. Really, I guess if you're going back pre-Silurian, really, you might lose a lot of the different types of terrestrial land plants that might give you a more restricted signature there. So that would need to be thought out. But I think it's certainly worthwhile trying.
All right, thank you.
All right, I see, Cornell, you posted a question in the chat. Were you able to unmute yourself and ask?
Yes, I can. Hey, Adam. Thank you for the overview. It's Cornell Alario here. So the question I have is that what's the range of the density of the material, the organic material? You say a few times that it's sorting by the density and things like that. But,
yeah. So
I mean, what will be the density range? And the second question is that, I mean, between the studies you did, you show us different areas. Is it significant organic material difference? I mean, in terms of the types that you saw? I mean,
so just to answer that first one, then not particularly. Although one of the things that we did was to keep it relatively simple in our categories of organic matter. So if I go back, what we did was to keep it relatively simple in terms of our types of matter. So there are other schemes out there for example, people will subdivide the Palyno wafers into like 10 different particle types based upon what different tree produced them, for example. That would then become very specific. And there's also, you can use the different types of spores and pollen again to give very high resolution types of schemes that might be applicable, say, to any one field or outcrop area. But in order to try and take a step back and make this a more generic methodology that could be applicable across space and time, then we kept that relatively simple. And then in terms of the density sorting, then what I've sorted them by density in here. I'd need to go back and take a look at the values again, but
just by what you remember, I mean, what will be like?
It's so the densest bits of wood. I've actually there's something like they're actually getting up to similar to quartz. It's like 2.5 grams per cubic centimeter, that sort of range. And then you get progressively lighter until you're like less than a gram per cubic centimeter already by the time you're down to these sorts of guys. And also, I think the I was highlighting density, but I think the shape is also quite an important control. So, for example, in the channel axis, we saw that it was these large, fairly spheroidal particles, whereas as you go out into the levees, then you see much more of this elongate bladed type material. So similarly, how you might think that micas, for example, are more easy to transport to the distal end of deposits as opposed to the feldspars or whatever.
Yes, yeah, thank you.
Any other questions from the audience?
Sure, I'll ask a question. Hi, Adam. This is David Morig. I have a question about the amorphous organic matter, and you said, well, largely marine, and I was just wondering how well we actually knew that. Awful lot of amorphous organic matter along in coastal wetlands and things like that.
Yeah, so you're very right to highlight that there's quite a few different kinds. And something that I've got down here that I call PSOM, the dark organic matter. A lot of people might call that amorphous organic matter as well. And that's coming from really degraded terrestrial material that's basically mush. But what I did, as well as observing the particles under transmitted light, then we were also using fluorescence on the microscope to differentiate the terrestrial structureless material that's usually inert and doesn't fluoresce, as opposed to the marine organic matter, which does show strong fluorescence under that type of light. So it's a little bit subjective as well, but there are other ways of differentiating those. So typically, your marine amorphous matter, it's actually the poop of phytoplankton. So it's like loads of little specks that what end up happening in the flows is that they aggregate and accumulate. So what you end up, I don't know if you can see it on the screen here very well. What you end up is with an aggregated mass of loads of little specks with like quite a fluffy boundary. And you can often see inclusions of other types of organic matter within that as well. They become encased in poop, horrible way to go. That you don't see with the degraded terrestrial material that has more defined boundaries within it. But, yeah, good question.
All right, thank you.
Hey, Adam. Hey, that was a nice talk. What's the highest level of thermal maturity that you included in your study, and what kind of limits is that going to present?
Yeah, so here the highest levels would have been from the French systems, from the Anot systems. So another thing that you can do with pollen and spores is look at the spore color index, and basically the darker the spores, the more they've been buried and heated up, right? And we were able to actually use this in samples that are going down to the estimates of about 3 kilometers burial. But I've previously also worked on systems in the North Sea, where we've got samples from 4 or 5 kilometers depth in the North Sea. The geothermal gradient is going to vary around the world, right? But at that sort of depth, it's still viable to use this methodology. So that would be equating to like 150 plus degrees of cooking. So it's relatively robust, but obviously you probably wouldn't want to do it on metamorphic, even relatively low grade metamorphic rocks. You'd want to stick to the more sedimentary type systems.
Thanks.
And I have a question since you're on the slides. As far as I know, there are some system that I was aware of that has this freshwater algae in the deep water system. Can you comment on that, why they are there and how they get there?
Yeah, so actually this guy, Botryococcus, it's one of the most common producers of hydrocarbons in the world. And they're actually produced in lakes, but they're very buoyant. And the inference, I think people have looked at it in detail, but the general inference is that particularly if you've got floods, then a lot of that material, because it's very buoyant and it's designed to float in water, with all these sort of air sacs that you can see in my schematic diagram, and then they're actually very easy to transport and wash out of the lakes and into your rivers and then into the marine environment. And they also occur in blooms. So if you often see lakes or swamps or anything that have all that green film on top, that's these guys. And that material in a storm or a flood can very easily get washed out into the deep marine environment. That said, in all the examples that I looked at, they were pretty rare. They weren't very abundant, which is another note, perhaps, just on the sort of, if you're considering the source rocks, then one of the obvious implications of this was that the actual turbidite mudstones aren't that great in terms of typically being dominated by your more terrestrial types of organic matter that might give you a type 3 kerogen if you're lucky. So it's other types of deposits that you'd probably be more interested in terms of your source rock.
So you think they had to initiate in lake system?
The freshwater algae, yeah, they would dominantly come from lakes more than rivers or anything.
Okay, thank you. Any other question from the audience?
If people want to give other questions later, you're always free to email me. I guess you guys have got my email contact, so happy to have a chat about anything.
Okay, I think I didn't see any other questions in the chat anymore. So that's conclude our seminar today. And thank you, Adam, again. You calling from Aberdeen. You guys are late in the afternoon already. So
time to drink some whiskey.
Thank you so much. And thank you everyone for attending today's seminar, and see you next week. Thank you guys.
Thank you.